Hi everybody, this is section 7.5, geometric mean and similarity in right triangles. And hopefully before you view this section, you will have viewed the video I posted from the YouTube channel Yay Math on geometric mean, because it'll help explain geometric mean a little bit better than just looking at the slides here. All right, so we have a theorem here, and it's the altitude of a right triangle. And what it says is the altitude from the right angle to the hypotenuse of a right triangle divides the triangle into two triangles that are always going to be similar to the original triangle and to each other. So they're all similar triangles. Really what you create, like you saw in the Yay Math video, is one large triangle, a medium-sized, and a small triangle. When you're looking at the three triangles created, or the original triangle and the two smaller ones created, it is helpful in order to compare sides and measures to orient all of the triangles the same way when you draw them, and that will help you write your similarity statement. As you can see here, we started out with triangle XYZ, and then the two smaller ones are triangles YWZ and triangle XWY. Right, so what we are going to do now is we're going calculating the geometric mean. And the geometric mean is different from, say, the arithmetic or the means you're used to when you take numbers, add them together, and divide by the number of items you have. That's called your arithmetic mean. Now we're looking at the geometric mean. And the geometric mean is directly related to our right triangle. If you draw a perpendicular from the right angle of the right triangle to its hypotenuse, so you draw the altitude, then the height of the triangle is exactly equal to the geometric mean of the two parts of the hypotenuse. Your geometric mean, the way that it is calculated, is you take, most of the times it's two positive, it has to be positive numbers, but you take the two numbers you're looking at, you multiply them together. So you would multiply your two numbers, we'll call them a of 1 times a of 2, and then you take the square root. This is what you're doing to find your geometric mean. Now, another way to look at it is to think of it as a proportion. So the x's represent your geometric mean of a and b. So if I have a proportion like this, when I go to solve it, it's going to be, right now, x squared is equal to ab, and then to get just x, you take the square root of both sides. So again, it's the square root of the two values multiplied together, which makes this the same as this, except I used a1 and a2 instead of a and b. All right, so here they want the geometric mean of 6 and 15. So again, we can calculate it. We can take the square root of 6 times 15. Or if we wrote it as a proportion, it would be 6 over x equals x over 15, or you could switch the numbers around. But when we solve it, if we do 6 times 15, we end up with 90. That's not 90, that's 19. We end up with 90 equals x squared, or the square root of 90. Now remember, when you have your radical, you do have to put it in simplest form. So that means you have to break it down, pull out your perfect squares within your radical. If you can't remember how to do this, I am going to post a video to help you simplify radicals to review that topic. But for my square root of 90, remember, I can break it down to the square root of 9 times the square root of 10, because the square root of 9 is a perfect square. The square root of 9 is 3, so we end up with 3 times the square root of 10, because I can't break that down. So the geometric mean of 6 and 15 is 3 square root 10. Now, next we're going to look at some corollaries to the theorem we looked at earlier about the altitude of a right triangle. And these corollaries can be a little confusing and hard to remember, but if you watched the video on geometric mean by Yay Math, you saw that they broke it down into something simple by just breaking up your triangle into the three similar triangles, and then you use proportions to find x and y, or the values. that's all I want you to remember. You don't have to remember these corollaries other than, you're familiar with them, you've seen them, so you know what it means. But to find the answer, we make it as simple as finding those three similar triangles, setting up our proportions, and solving. So this corollary says the length of the altitude to the hypotenuse of a right triangle. So they're saying that our altitude here, right here, this is the geometric mean of the lengths of the segments of the hypotenuse. So it is the geometric mean of AD and BD. So CD is the geometric mean of AD and BD. And here we have corollary 2, which says the altitude to the hypotenuse of a right triangle. So again, we're still talking about CD. It separates the hypotenuse so that the length of each leg of a triangle is the geometric mean of the length of the hypotenuse and the length of the segment adjacent to the leg. So here, that altitude, it separates that triangle into those three similar triangles. And when it does so, now we're talking about the legs of the right angle. And each leg of the triangle is the geometric mean of the length of the hypotenuse to the length of the segment of the hypotenuse. So what we're going to look at here is for the first one. All right, AC is one of my legs in my right triangle. It is the geometric mean of the entire length of the hypotenuse plus the part that it is connected to, so AD. Okay. If we look at the other leg, CB is the geometric mean to the entire length, so AB, and then also to the segment that it's connected to, so DB. And again, you can remember these or know how to work with those right triangles and the similarities using your proportions, and you get the same answer. And this slide just again goes over the two theorems that we talked about, or the corollaries. You have your hypotenuse, or your altitude, that is the geometric mean to the two parts of the hypotenuse, or you have the legs that are the geometric mean to the hypotenuse and the part of the leg that is attached, or the part of the hypotenuse that is attached to the leg. All right, so now what we're going to do is we are going to find the values of x and y. And again, what I'm going to do is you'll see the geometric mean, but what we are going to do is we are going to draw our three right triangles. So I'm going to start off, I'll have a big one. And again, I apologize for my beautiful drawing skills. We'll have our medium one, and we'll have our small triangle. We got to figure out our measurements. So for the large triangle, I always call it the short leg and the long leg. The short leg we know is x. We don't know the long leg, but the hypotenuse, which is right here, is 16 because it's 12 plus 4. All right, next we're going to look at the medium-sized triangle. So when we look here, the medium-sized triangle, here's my right angle. I know both the legs. I know the long leg is 12 and the short leg is y, but I don't know the hypotenuse. And then let's look at the little triangle here. And this is one where I know all the measurements. The right angle is going to be right here because there's a right angle right next to it. And so it looks like the long leg is y, the short leg is 4, and the hypotenuse, which is opposite that right leg, is x. So now that I have all my measurements, I can find x and y. Doesn't matter which one we start with. Let's start with x. So on my big triangle, I know I have the ratio of the short leg to the hypotenuse. So that is going to be, So short leg to hypotenuse would be x over 16. And then we'll go to the triangle where we know both those measurements again. So it's the small one. We have short leg over hypotenuse. So it's going to be 4 over x. Again, if you look at this, we have those x's catty-corner to each other, which gives us our geometric mean. We multiply, we get x squared equals 64. Take the square root of both sides. So x is going to equal 8 for this first one. And now we need to find y. So to find y, we're going to go to the middle triangle, and we know we have long leg to short leg. So when I write my proportion, I'm going to do 12 over y equals, and then I go to the other triangle where we know it's the small one, so we're going to do long leg over short leg. So we would do y over 4. Again, we have those variables catty-corner to each other, setting up our geometric mean. So we get y squared equals 48. Take the square root of both sides, and we end up with y equals the square root of 48. But we do need to simplify that, break it down. The largest perfect square in 48 is going to be 16. So I can break it down and make it the square root of 16 times the square root of 3. And the square root of 16 is 4. So my final answer is y equals 4 square root 3.